Okay, we want to prove that adding a multiple of a row doesn't change the determinant of a square matrix. So let's just write a general square matrix. And I'm actually not going to write a general square matrix. Okay, here's our matrix. And the determinant is then A11 times the determinant of the minor minus A12 times the determinant of the 1,2 minor plus A13 times the determinant of the 1,3 minor. What you do? So that's what the determinant is. Now, we don't really need to have written this out, but I wanted to write it out just for perspective. Okay. So now, let's just add a multiple of the second row to the first. Okay, so okay. Now I'm going to let C be the multiple of the second row that gets added to the first. So the new first row will just have the A11, A12, A13 that we already had. And then we're going to add C times the A21, C times the A22, C times the A23 to the corresponding numbers in the first row. And then we just have A21, A31, A22, A32, A23, A33. And now we're going to expand this determinant. Okay, so we'll have to come up to here, of course, working backwards around the board. Okay. And that's going to be going to be A11 plus C A21 times the determinant of the corresponding minor minus this times the determinant and then A13 plus C A23 times the determinant of the final minor, which would be A21, A22, A31, A32. Okay, well, there's a more elegant way to do this. I might have been better off doing that. Okay, A11 times this determinant, A12 times this determinant, A13 times this determinant is just what we wrote out here, the minus one, the A12. So that is the determinant of our original matrix, which I didn't call A, but I should. So this is the determinant of A here. And of course, if I just take these three factors times the determinants of the minors, I just get this. And then it's going to be plus C times the determinant of what? Okay, well, A21 times this determinant, A22 times this determinant, A23 times this determinant, lined up as it is, you can convince yourself that that is simply the determinant of A21, A22, A23. Which is this. Okay? So, again, I'm not going to write out the details because of time and other factors. But these three factors times these three determinants are just this. There's your determinant of A. And to that you add C times the determinant, well, it's going to be A21 times this minus A22 times this plus A23 times this. And it turns out that's just the determinant of this matrix. And that's just the determinant of A, because anytime you have two identical rows, you know the determinant is going to be 0. Okay, now there are more direct ways to prove this, and I'll probably go ahead and mention them. We know the determinant of this matrix is 0 because if we subtract, if we do a row reduction, we're going to end up with a row of zeros. We're going to be subtracting this row from this one. That's going to give us a row of zeros, and that's it. The determinant is 0. Okay? And we can also prove the same result more directly by row reduction. If I subtract C times the second row from the first, C times the second row of this matrix from the first, I'm going to get rid of all these, and I'm going to be back to my original matrix. So even more directly, with this matrix, we subtract C times the second row from the first, and we get the original matrix. So we didn't have to go to the trouble of writing all this stuff out, because we know that when we add one row to another, we don't change the determinant. So there's no change in the determinant. So that's two ways that we could do this. This is going to be a little more general because I just did this for a 3x3 matrix, okay? How would you extend this, which is already a little bit messy, to an n×n matrix? Well, it turns out it's not that difficult. It's not that sloppy. But you have to use a little more notation. But you do know that no matter what this no matter what the dimension of this matrix, if I've added C times one row to another, a multiple of one row to another, I can inverse that operation without changing the determinant. And if I inverse that operation, I'm back to the determinant of the original matrix. So, this is much more elegant than this. I would accept something like this, a good attempt at this, for a good partial credit. I'd accept this for full credit if you do all the argument. But if you want to save yourself time, you do this. You simply quote the results of row reduction.